Hi everyone, welcome to our sixth lecture of CSC 110. In this lecture I'm going to be introducing a new topic called encoding. But before I do, let's summarize everything that we've done in the course up to this point, because last lecture was kind of a high point in the course. I promised you that I would build for you a mechanical mind. That was that adding machine that I designed for you in the last lecture, and that's complete now. So we've got a lot of information and a lot of knowledge about how computers work, and we can now move on to more practical things with that information, and that's what we're going to start to do in this lecture. Okay, so let me summarize. Going way back to the earliest lectures, I showed you how binary numbers or binary can be used to represent numbers. Okay, so that means like if you've got some value, like this many fingers. Okay, like in decimal we would say 5, but in binary we would say 101, and that would be a representation of this many fingers. Okay, and basically there what you needed to know was if you had a number like that, okay, 101 101, okay, you can say, well, how much does that represent? Well, our minds don't work in binary, so I taught you how to convert from binary to decimal, and basically you just go from right to left and you say, okay, that's a 1 in the ones column, there's no 2's, there's a 0 in the 2's column, there is a 1 in the 4's column, a 1 in the 8's column, there's no a 0 in the 16 and a 1 in the 32. And so if you put that all together, 1 plus 4 plus 8 plus 32 gives you 45. And so this number right here, 101101, actually represents the value 45. Okay? So that was the first thing I taught you. The next thing I taught you is how to do binary arithmetic, okay, and also binary logic and binary circuits, okay. I'm going to do it in a slightly different order right now. I'm going to start with the logic and build up the arithmetic with that. And so the first thing we needed to learn was how to build something that could add 2 bits, okay, which the device was called a 2-bit adder. And basically if you have 2 bits, and here they're being represented with A and B. So A could be either 0 or 1, B could be either 0 or 1. But when you add 2 bits, you get 2 bits coming out. One of them, the one on the right hand side, we call the least significant figure, and the one on the left hand side here, we call that the carry, okay. And so like if you're in a situation like you do 1 plus 1, you'll get 2 binary bits coming out, okay. 0, that's your least significant figure, and 1, okay. So 1 plus 1 is 0, carry 1, and we were able to replace that addition with 2 logical operators, exclusive OR and it turns out that the least significant figure is obtained from the 2 inputs with exclusive OR, and the carry is obtained from the 2 inputs with AND, okay? And so you can see how that works here. You can see that the least significant figure here is 0, and sure enough, if you do 1 exclusive OR 1, you get 0 as your answer, okay? And the carry is 1, and again, if you do 1 and 1, you get 1 as your answer, okay? So basically, binary addition is the equivalent of both exclusive OR and AND, okay? So when I first introduced this, I just taught you how to add, okay? But now, not only do you know how to add 2 bits, but you also know the logical operators behind that addition, okay? Then the next thing I taught you how to do was to do 3-bit addition, and the device for that was a 3-bit adder, and it was made up of 2 2-bit adders plus an OR gate. And basically, it was based on the idea that if you had to add 3 bits, which we did when we did long addition, I'll show you that in a minute, okay? But when we did long addition, sometimes you would be adding the 2 bits, but you would have a carry from the previous column, and then you'd have to add all that together, okay? And so the way you can add 3 bits is in 2 steps, okay? So the first step is you add the first 2 bits, like you would add, the 0 plus 1 first, and then you would add in the 1 later, like that, okay? In fact, I could probably indicate that by using brackets. So first you would add the 0 plus 1, and then you would add in the 1 later, okay? So the first step is, you take A and B, so that's the first 2 bits here, okay? And you add them together just like you did before, and that's basically your 2-bit adder right there, okay? 2-bit adder, all right? So, that's the abstract way of writing it. A plus B is equal to a least significant figure and a carry. Now here I called it C1 and L1 because there's going to be 2 2-bit additions. This is the first of the two, okay? And so, you know, like if we're doing 0 plus 1, so we're doing like 0 plus 1 plus 1, we would do the 0 plus 1 first. There's the 0 plus 1, and what's that equal to? That's equal to 1 carry 0, okay? And I'm not going to show you how that breaks down into the exclusive or NAND, because I think you know how that, you've seen how that works already, okay? The next step would be to do another 2-bit addition. Now, the A plus B have been already added together, and there are these 2 bits, C1 and L1. And now we're going to add in D, which is the third bit here. That would be that 1 there in this example, okay? And when you add, remember you align things up so that all the bits are aligned. So that D aligns with the L1, okay? And so basically you add D and L1 first, and the carry is just sitting there in the column to the left, okay? And then when you add D plus L1, you're going to get C2 and L2. So L2 is the least significant figure from the addition of D plus L1, and C2 is the carry. Okay, so again, we add D plus L1, and we get the least significant figure L2 and a carry C2, like that, okay? And I call them C2 and L2 because this is the addition from the second. Those are the carry and least significant figure from the second addition. But they're still the carry from the first addition, and we can combine it with the carry for the second addition, and that's what we do there. And once we combine those two, we get our answer, okay? So let's go through that with this example of 0 plus 1 and then plus 1. So if we do 0 plus 1 first, because we're doing this in 2 steps, so the first step is 0 plus 1, we get 1 carry 0, okay? All right, so that A plus B, that gets reduced to 1 carry 0, okay, or 0, 1 there, okay? Now what? Well, you don't add the 1 to the carry, you add the 1 to the least significant figure, so let's group those together. The carry is still there it is, okay? And then you go 1 plus 1, okay, and 1 plus 1 is 0 carry 1, there it is, all right? And I've aligned these so you could see that L2 is 0 and C2 is 1, all right? And so once we've added in D to the answer that we got from adding A and B, we get 1, 0 or 0 carry 1, okay? And there's still the 0 carry from the first addition, and we add that into the second carry. So here's the first carry, there's the second carry, and when we add 0 plus 1, we get 1, and there's our answer, okay? And sure enough, if you do 0 plus 1 plus 1, it's 0 carry 1 or 1, 0. Okay, and there were more examples that I did last time, but I just wanted to remind you how this 3-bit adder worked. But basically, the 3-bit adder was first a 2-bit addition, and then there was a second. Yeah, can you see that? Yeah, you can. All right, move that down just a bit. There's a second 2-bit adder step, and then that final addition over here. Okay, 2-bit adder. Okay, and then that final addition here required an OR gate. Okay, that was this addition here. And you go, why did you need another 2-bit adder there? Because you can never have that both C1 and C2 are both 1, and so it's sufficient to just use an OR. Okay, and so there you go. So that's how you did 3-bit addition. Admittedly, that's the hardest one to get your head around. Okay, and so once we had 3-bit addition, then we could build this full adder, and the full adder was basically a 3-bit adder for every column, plus the cascading carry. What I mean by that is you would add 2 columns, and then whatever carry you had from that, you'd send it into the 3-bit adder for the next column, okay? And again, I showed you that circuit last time, so I'm not going to do that again. But basically, there, you had something that looked like this. You had your first number, and I just did 4-bit numbers, okay? You could do as many as you like, but you know, you have to limit it to something, so I limited it to 4. And your first number, you know, I called the bits from right to left, A1, A2, A3, and A4. So you might have a number like this, okay? And now reading left to right, which is the way we usually read, that's like 1, 1, 1, 0. That's like 14 in decimal, okay? And we might add that to a second number, and the second number I called it, you know, again from right to left, the bits are B1, B2, B3, B4, and so here they are, okay? So like B1 in this case is 1, B2 is 1, B3 is 1, and B4 is 1. And then what you would get out as an answer is a bunch of least significant figures from the addition, plus an overall carry, and we call that overall carry the overflow, okay? And this is basically 14 here in binary, and I'm sorry, in decimal. And if you convert that to a decimal, it's 7. So basically, we're doing 14 plus 7. And if you convert that, that's 21, okay? And there you go, all right? Now, summary from of last lecture, okay? Now, the only other thing you need to know to understand what I'm going to do next is how the logical gates are made out of these transistors. So I had that little bit of an aside where I showed you that if you put two transistors in series, that's one after daisy chained after another, you basically got a NOR gate. And if you put them in parallel, you got a NAND gate. And then you could use a third transistor to invert that, because a single transistor is like a NOT. And that showed you how you could build an AND gate out of three transistors, okay? And you can build an OR gate out of three transistors. I skipped the exclusive OR because I didn't want to overwhelm you with too many different possibilities, okay? And there are lots of gates besides just the ones that I've given you, but they can all be made out of transistors. But, you know, we skipped the exclusive OR, but the exclusive OR can be made out of 4 transistors, and the NOT gate can be made out of 1 transistor, okay? So there you go. There's a summary of everything we've done up till now, plus with emphasis on the last lecture. Okay, now let's apply that to some real hardware, because now we can start to say something about what, you know, real computers are like. And this actually has some like monetary implications, so you'll want to pay attention to that, because it's actually going to tell you a little bit of how to like buy how to, you know, what kind of computer to choose when you're buying computers. All right, so let's start off by asking a very simple question. Okay, so how many transistors does it take to make a full bit adder which is 4 bits wide? So this word 4 bits wide, you might wonder, well, what do I mean by 4 bits wide? Well, if you go back to, you know, my full bit adder here, okay, I was adding, my first number was made up of 4 bits, okay, and my second number is made up of 4 bits. Now the answer will turn out to be 5 bits, but, you know, computers, they're made with these things called buses, which are basically, you know, just like bundles of wire that connect one component to the other. And most computers today are made up of bundles of 64 bits, okay? And so the adders there, the full adders there, are actually 64 bits wide. It means that you can add a binary number which is 64 bits plus another binary number which is 64 bits, okay? Now remember, when you do that, you'll get 65 bits as your answer, but you got to throw away the overflow. And that means that the entire computer basically works with 64 bits. Okay, everything is 64 bits wide. All right, that's what we mean by wide. So, you know, if your computer can only handle, you know, a 4-bit number plus another 4-bit number, first of all, that would be a pretty useless computer, because you can't do anything over 15, right? But, you know, if that's all you could do, you would say, well, that you know, that adder is 4 bits wide. Okay, and that, like I said, most computers are actually 64 bits wide, which means that they can add a binary number up to 64 bits plus another binary number up to 64 bits. Okay, now. By the way, that's a huge decimal number. I think it's got like 34 digits in it if you converted it to decimal. So it's absolutely huge. Okay. Anyhow, so, you know, if you've got, you know, 4 bits wide, that means that you can add 4 columns, as I just said. Now each column, okay, is going to require a 3-bit adder. All right, and each 3-bit adder is made up of 2 2-bit adders and an OR gate. All right. And each 2 2-bit adder is made up of an AND gate and an OR gate. Okay, now why did I break it down like that? Okay, that's the turtles within, on top of turtles, on top of turtles. Okay, so if we just kind of like zoom in, zoom in, zoom in, zoom in. At the biggest level, we have the full adder, okay, 4 bits wide. Then each column is a 3-bit adder, and each 3-bit adder is 2 2-bit adders and an OR gate, and each 2-bit adder is an AND and an exclusive OR gate. And the reason I broke it down that way is because now we can actually do an estimate of how many transistors it takes to make a 4-bit wide adder, full adder, okay? And so for the 2-bit adder, because you need an AND and an exclusive OR gate, that's basically 3 plus 4, or 7 transistors, okay? So 3 transistors for the AND gate, 4 transistors for the OR gate, for a total of 7 transistors for a 2-bit adder, okay? For the 3-bit adder, remember the 3-bit adder is made up of 2 2-bit adders, okay? And so you've got 7 for your first 2-bit adder, another 7 transistors for your second 2-bit adder, and it also has an OR gate, so there's going to be 3 transistors for the OR gate, and you add them all up, you're basically going to have 17 transistors for each 3-bit adder. Remember, a 3-bit adder is a column, okay? And we've got 4 columns in our adder, and so each column requires 17 transistors for a total of 68 transistors, okay? Now, older computers were 32 bits. Some older phones were 32 bits, okay? But nowadays, most computers are 64 bits, okay? And so if you wanted to build a 64-bit wide adder for a modern computer, each column is basically, a 3-bit adder, so that's 17, and you're going to need 64 of them for a total of 1088 transistors. Okay, so there you go. That's just the adding part of a computer. Now, computers do a lot more than that, obviously. Okay, but they at least have to be able to do addition, subtraction, multiplication, division. All right, and we just in this course we just looked at addition. Okay, and now let's ask ourselves a very simple question: how big is this circuit? Okay, and you're going to be surprised at how incredibly small it is. Okay, so the first thing is that transistors can be as small as 0.2 nanometers in size. Okay, now I got to be honest, I don't know if that is the current size of transistors, but that's assumed to be kind of the ultimate limit, and we're very close to that. Okay, so if you look up and you see that a transistor is, even a 1 nanometer, okay, don't be surprised. You say, well, I'm giving you wrong information. No, this is kind of a limit about how small you can make transistors before you just can't make them any smaller. I mean, they have to be made out of atoms and molecules, okay? And so, and I didn't really describe how they're made, but if you don't have enough atoms and molecules, they just won't act like a switch. And if they don't act like a switch, they're not a transistor, and so it doesn't work, okay? So this is kind of like the limit, okay? And we're going to talk about Moore's Law in just a second, okay? Now, what does nanometer even mean, okay? Like I said that like you should know what it is. Well, you should know what a meter is. It's about 3 feet wide, okay? It's hard for me to show you on the screen, okay? But, just imagine a meter, 3 feet, okay? And a billionth of a meter, just divide this thing up to a billion pieces. That's 1 nanometer. 1 nanometer is a billionth of a meter, okay? A billionth is like a 1 followed by 9 zeros, okay? So, 0.2 nanometers is like 0.2 billionths of a meter wide. This is absolutely tiny. In fact, it's so small, it's really hard for us to imagine how small it is. So I said, well, what can you compare that to? So I decided maybe we can compare it to a human cell. And a typical human cell, I just looked this up, is about 100 micrometers. And you go, what's a micrometer? A micrometer is a millionth of a meter, okay? So that's like a 1 followed by 6 zeros. So nano is, a billionth. Micro, the symbol right here, is a millionth. So, a millionth of a meter is 1,000 times bigger than a billionth of a meter, okay? Now, it's even bigger than that because it's 100 micrometers wide, okay? So a human cell is about 100 millionths of a meter wide. Now, if you converted that into nanometers, that would mean 100,000 nanometers, okay? So that means that across a human cell, you could get 100,000 transistors, all right? A human cell, which is a very, very tiny thing, you can only see it under a microscope, even that is huge compared to a transistor where you can get like 100,000 transistors, okay? Oh, sorry, no. That's if the transistor were 1 nanometer, but if the transistor is 0.2 nanometers, that actually turns out to be 500,000 transistors wide, okay? So that's pretty much the limit. And we're talking end to end, okay? We're talking incredibly tiny little devices here. All right. So how many does it take? How many transistors does it take to make a 64 bit wide adder? Only 1088. Okay. So this is unimaginably small. You could basically put a computer, at least a calculator within a human cell. Okay. Once again, this number here, 0.2, that might be smaller than our actual transistors today. Okay, and there's some transistors which are huge, okay, but as far as the transistors that are on the central processing unit of the computer, that's what we think the limit is. We won't be able to ever get smaller than 0.2, okay? And I've been seeing numbers like 1 nanometer. All right, 0.2 is like five times 1/5 the size, sorry. Okay, so we're not that far from our limit. Okay, so yeah, the computers are they have been shrinking over time. Okay, and even my cell phone here is more powerful than the supercomputers I used to use when I was a graduate student in at Guelph, Ontario. Okay, University of Guelph, and we got to use these supercomputer a Cray supercomputer, which is at the University of Toronto. And this was a powerful machine, except that, it was many years ago, and this thing is now more powerful than that. So that's just mind-boggling, okay? And will this continue? Well, I'll tell you about Moore's Law in a minute, but before I do, let me just tell you, a little bit of the history of the hardware of computers. Okay, so, if we go back to the 40s, computers were not made out of transistors. Okay, transistors were discovered in the 40s, and they didn't come into really being used until the 60s. Okay, but the first switches, because remember, all those gates are transistors, basically a tiny little switch. Okay, and all those gates are just made out of switches. So you say, well, do I have to make them out of transistors? No, any switching mechanism will work. In fact, I gave you the analogy of like hoses and valves. Okay, you could actually build a computer out of hoses and valves, where your valve is your switch. Your valve is either allowing the fluid to flow through, the water to flow through, or it's not. Okay, so before there were transistors, our switching mechanisms were relays. Okay, I'll show you a relay in a second. And we still use relays. We just don't use them in computers. Like if you ever you use your washing machine and you hear clicking, okay, between the different cycles of the washing machine, those clicks are basically relays turning on and off. Okay, that's what they are. Okay, and you can imagine building an entire computer out of these relays. Now they're huge, and so you wouldn't be able to build a very practical computer, but you could build something with it. Okay, and that was like the 1940s. By the 1950s, we had these things called electronic tubes. Okay, and I was born in 1964, so I can barely remember these things. Okay, and they were basically the switching mechanism, and I'll show you a picture of them in a minute. But then transistors started to hit the market, and the first thing that they started to be used in were transistor radios. Okay, and this was like in the 60s and into the 70s. Okay, people would no longer have huge radios, which were like, they were the size of like a cabinet or something. Now you could have a small little portable radio which ran off of a battery, and these were your transistor radios. Okay, now the transistors there were individual units. Okay, so they were like little tiny cylinders. Again, I'll show you a picture in a second. They were these tiny little cylinders, and each one was a transistor. They're still huge, like they were about 1 millimeter or 2 millimeters in size, nothing like the nanometer size. Okay, and so you still couldn't really build very powerful computers out of them because you'd have too many transistors. And then starting in the 1970s, we discovered this new technology. They're still transistors, but we could actually like put these transistors on a silicon wafer. And the way it worked is you would take, silicon like as a wafer, and you would actually like squirt a little, you'd have like a tiny little needle, and you would squirt like a gallium and arsenic and all that across it, maybe a little bit of gold, and by just painting on top of the silicon wafer, you would actually paint your circuit on there. And these are called integrated circuits, and they got the transistors on those got progressively smaller over time. Okay, let me just show you some pictures of relays. Okay, so these are relays here. Okay, and you can see like they look like I don't know, like something that would plug into a wall. But basically, one of the leads here was used to like either open or close the relay, and then the other leads were used to allow the current to flow through. Okay, so they were basically switching mechanisms. All right, so there's relays. The next thing that computers were made out of were these tubes here, and you can see here they're like I don't know, like elongated light bulbs, and they actually did glow in the dark because there was electricity that flowed through them. And they have multiple leads on the bottom here. You can see on this one where my cursor is, they had multiple leads on the bottom, and they would either one of the leads would either allow current to flow or not allow current to flow, and that's how they would switch. Okay, and let me see if there's any that are glowing here. Not really, but that's how these tubes worked. Okay, and they were like light bulbs in the sense that they got hot and they burnt out and so on. So the next thing were individual transistors. And this is what individual transistors look like. So you can see here, like, take a look at the very first one here where my mouse cursor is. You can see they have 3 leads, okay? Remember, transistors have 3 leads. One of them is the switch, okay? So if you apply electricity, it's probably the middle one. It's called the base, all right? But if you apply electricity to the base, then the other 2 don't allow electricity to flow through them. But if you don't apply electricity to the base, then they do. Okay, and so basically that's how you switch them on and off. Either you apply electricity to the base or you don't. And if you do, then there is no flow, and if you don't, then there is flow. Okay, and so you've got a switch. But again, they're still too big. I don't know if there's a picture here. Usually they put these things beside a coin. There you go. You can see here. Like that's how big a penny is, and you can see the little transistors that are beside them. So they're still pretty small, but if you needed 1,088 of these, that would add up, and it would be way too big to put inside of a computer. Today there are billions of transistors on a silicon wafer. Okay, so we have to get them smaller than that, and the way they did that was through these integrated circuits here. And this isn't, you can't actually see the silicon wafer here. All you're basically seeing, like if you take a look at these, and you've probably seen electronic boards with these integrated circuits on them. You can see they have all these leads. Okay, the silver here, each one of these are leads where electricity can flow through them. And then it looks like a plastic box, but the plastic is just a coating to protect what's on the inside. In fact, this one over here on the left-hand side with a lot of leads, okay, that's probably a CPU, which has been soldered into a motherboard. Okay, and the motherboard is basically just the board that holds all the integrated circuits together. Okay, so what does a silicon wafer look like? Well, here's oh, what happened here? Oh, there they are. Okay, there's the silicon wafers, and you could see that like a blank silicon wafer would, before you actually print the integrated circuit on it, would just be kind of like blank looking, like this one right here. Okay, but what they do is they'll paint these integrated circuits on them. Okay, and you can see this one here, the one that's kind of like colorful here where my cursor is, and you can see how it's got a bunch of squares on it. Each one of those squares would get cut out, and then they would be put inside of like one of those plastic shields, and that's basically your integrated circuit. Okay, and each one of these like little squares here has billions of transistors on it. Okay, and that's what powers your computer. All right, now I didn't just do that, I didn't just tell you this for no reason at all. One of the predictions about computers and how fast they would grow, or conversely how quickly the transistors would get, was actually a law called Moore's law. Okay, now it's called a law, but it's not really a law like the law of like physics laws. Okay, like say the law of gravity. Okay, if you drop something, it falls. It always falls. The law is never broken. Moore's law should never have been called Moore's law. It was for whatever reason. It's just like this guess. Gordon Moore was one of the co-founders of Intel. Okay, and so like Intel Inside. Okay, the company that builds the chips that power a lot of computers. Okay, and he made this prediction. He predicted that the number of transistors per unit area on an integrated circuit would double every 1.5 years. Now, actually, he said every 2 years, but it turns out that it's closer to every year and a half. Okay, so his prediction was slightly wrong, but he was right in the sense that the technology would grow exponentially. And I'll explain what exponential means in just a second. But let's see if we can understand the law here, because this is going to have financial repercussion. Okay, he basically said that the number of transistors per unit area. Well, what does this per unit area means? It means, like just say we're going to look at a square inch. Okay, we're going to look at a square inch this year, and you're going to ask the question, how many transistors can you get on this square inch this year? And if we were like back in the 70s, you might say only 1,000. We can only get 1,000 transistors on this square inch of silicon, okay, this year. In a year and a half, you would be able to get twice that, 2,000. Okay, in a year and a half after that, it'd be twice that, which would be 4,000, then 8,000, then 16,000, and so on. Okay, now the reason this is really important is because this doubling every year and a half means that you have exponential growth. And exponential growth, it looks like something that starts slow, but it gets faster and faster and faster and faster and faster as time goes on. Now, it doesn't just occur in computers. It also occurs, say, with bacteria growth. Okay, so if you have bacteria or virus, and you have some virus in your nose, and maybe you only have a few hundred viruses. Okay, now a lot of those will die, but one of them will produce two. This is more true of bacteria than viruses. Let's do bacteria. Okay, one will produce two, and then each of those will produce two for four, and each of those will produce four for eight, a total of eight, and then 16, then 32, then 64, and so on. Okay, and you might say, well, okay, so what? Well, at first it's slow, but then it gets faster and faster and faster. Okay, and once you're like up to, well, let's this is a nice little paradox that people say. Suppose I say to you, give me a penny today, then tomorrow give me 2 pennies, then the day after that give me 4 pennies, then the day after that give me 8 pennies. Okay, and then I ask you, how much are you giving me at the end of the month? It would actually be 2 raised to the power of 32. Okay, why? Let me explain why. Okay, so you'd have 2 pennies on the second day, but then you'd have 2 pennies on the twice that on the third day, which is 2 times 2, and then you'd have twice that on the next day, and then twice that on the next day, and then twice that on the next day, and then twice that on the next day. Every day you're multiplying by 2. After 32 days, you'd have 2 times 2, 32 times. Now, when you multiply 2 by itself 32 times, you're going to have the number 2 to the exponent 32. And if you do that on your calculator, that's going to be 4 billion. I'll give you the exact number in just a second. I'm doing it here on my calculator. Okay, it turns out to be this number here, and there it is. So yeah, on the first day, it's 2 pennies, then 4, then 8. But then by day 31, I have 32 here, okay? By day 32, it's 4 billion pennies, okay? Now, 4 billion pennies is, it's a lot of money. So what happened? It started off slow. You could say, look, you can give me 2 pennies. That's not much. And the next day is 4 pennies. Come on, you can give me 4 pennies. And it's not going to hurt your bank account, and then 8 and so on. But by the time you get to the end of the month, it's going to be huge. Okay, now this is what's been happening with the number of transistors on a unit area, say a square inch. Okay, they've been doubling every year, and that means that computing power has just exploded. Okay, so our computers of, like, say, the 80s and 90s, they were nothing. Okay, they're nothing compared to, say, even this. Okay, and your cell phone is already more powerful than any of the computers from the 90s because of this continuous doubling of Moore's law. Okay, now above I said to you, it's not clear that we're going to be able to get to transistors that are smaller than 0.2 nanometers. Okay, that's probably going to be the limit of how small you can make a transistor. And so Moore's law says, well, they keep getting smaller and smaller and smaller. And so that's why it's not really a law, because it's going to come to an end, and it's probably come to an end actually. So we're not going to be able to make transistors much smaller. So Moore's law is kind of coming to an end. But nonetheless, it has had some repercussion in terms of the how much computers cost. Okay, and let me explain why. Okay, so basically, one of the things that you conclude from Moore's law is that with the same amount of money, the amount of computing that you get if you wait a year and a half is going to be double. So, in other words, if you say, look, I only want to spend $1,000 on a computer, if you bought that computer today, you'd spend $1,000. If you waited a year and a half, you'd buy the computer for $1,000, another computer in the future for $1,000. That computer a year and a half in the future would be twice as powerful as the computer that you have right now. Okay, so with the same amount of money in a year and a half, you'd buy twice as much computing power as you do today. Okay, again, I'm not sure that's going to be that's so true anymore. Like I said, we're kind of coming to the end of Moore's law, but there's still some truth to it. Okay, so yeah. Now, what about the converse of that? The converse of that means that any computer that you buy today is going to be worth half as much in a year and a half. So they depreciate very quickly. And this is why I said, this has some, repercussions in terms of finance. So if in 2018 you bought a really powerful computer for $2,000, then a year and a half later, which would be like halfway through 2019, that computer would only be worth $1,000. Okay, and then if you wait another year and a half, like to 2021, this year, it would be worth 500. And if you waited another year and a half until the middle of 2022, that computer would be worth, $250. So, in not too long here, in just, a few years, that $2,000 computer isn't worth that much anymore. Okay, and so in 4.5 years, it's basically dropped to 1/10 of its original price, a little bit more than 1/10 of its original price. Okay, is that still happening? It does seem to be still happening, but I think that we are starting to get to the limits of Moore's law. Okay, so well, there it is. This is Moore's law. All right, and unless you have money to burn, the lesson you should get from this is never buy like a high-end computer, because if you buy a high-end computer, the depreciation is going to make you lose money very quickly up front, and you say, well, why did I spend all that money for? I should have waited a little bit. I could have bought myself an even more powerful computer. But if you have money to burn, you can. Okay, like people that want the latest gaming machine. But otherwise, if you're just buying a computer, you should probably buy a low end, mid to low end. Okay, and the reason is in a few years you're just going to want to replace it anyhow. Okay, now Moore's law for computers, like desktops, that's probably ending. Okay, for laptops, but for phones, yeah, phones are still getting more powerful. They're still getting more powerful. Okay, so there you go. One last thing, and then we'll move on to encoding, and that is beware of magical marketing. What they'll do is, especially Apple does this. They'll produce the next phone and they'll tell you this is the greatest thing since sliced bread, and they'll say, buy this thing, and people that are like aficionados will go out and buy them when really their old phone was probably just as good. Okay, they'll say, your life can't possibly have meaning unless you buy the latest iPhone, and some people will buy the latest iPhone. The other thing that's annoying, and they have been caught doing this, so I'm not saying anything that isn't known, but with the upgrades run worse and worse and worse on the older phones, and that puts pressure on people to upgrade their phones. Okay, so yeah, there's still growth in the hardware field, but I think it is coming to an end, as I said. Okay, that ends all of the discussion on the hardware, and let's turn to this next topic, which is encoding. Okay, now what is encoding about? Sorry, let me put this down so you can read it. What is encoding all about? Okay, so there's a couple of things that happened in the digital revolution. Not only have we discovered how to build these thinking machines like I showed you, but we've also come up with something else, and computers are not just computers anymore. Okay, so we say computers, compute, what do you think of? You think of like a glorified calculator or something like that, but we're not using computers that way now. Okay, if anything, they're more like communicators. All right, we use them to communicate. We text with them. We watch YouTube, do social media, all sorts of things. Okay, so they're more of a communication device, although they still do a lot of computation. But anything which is communication means like the transfer of information. And so we have discovered in this digital age how to take any human information and convert it into a sequence of ones and zeros. Okay, so all information, all right, not just numbers, which is what I did above. Okay, if you go way up to the beginning here, up here, I said, look, one of the first things I did was show you how you could do a binary representation of numbers. So, like the number 5 in binary is 101. Okay, that's a binary representation. But now I'm making a stronger claim. I'm saying that any information, okay, things like the letter A, okay, the English letter A, okay, or actually this entire page. This entire page is encoded as a sequence of ones and zeros. Okay, the voice that you're hearing that's coming through YouTube, that was encoded as a sequence of ones and zeros. The picture you're seeing, the video you're seeing, that's encoded as a sequence of ones and zeros. And you can ask the question, how in the world is it that, say, this letter here that I've highlighted, that H, how is that H a sequence of ones and zeros? Okay, or if it's a picture, and I'm going to show you, I'm going to go as far as colors in a picture, and I'm not going to go any further, but you go, how in the world can you encode like a color as a sequence of ones and zeros, okay? And I'm not talking about just particular colors, I'm talking about all humanly visible colors. And yeah, you can encode all humanly visible colors as a sequence of ones and zeros, and you go, how do you do that? And of course, once you can do colors, you can do pictures, and you can do audio, and you can do video. So I'll go up to pictures, but I won't do audio and video because I don't want to get too far. It's important that you see how that it can be done without necessarily knowing all the details of how audio is done and video is done and so on. Okay, once you've got that idea, then you have an appreciation of how digitization works, and that's probably going to be important in your field because there's going to be things like computers nowadays do diagnostics for x-rays, and the x-rays themselves are digitized, okay, and they're transmitted through the internet, okay. I mean, you can still get them on a CD or something like that and they'll be digitized, but no one walks around with like film, x-ray film. Everything is just done as digitization, and so that's basically a sequence of ones and zeros, and computers are actually now able to do an analysis of x-rays, sometimes better than doctors can, because they'll see things that doctors can't. Okay, they can process a lot more information. Okay, so that's what encoding is all about, and as I said, it's basically this other aspect of the digital revolution that we're undergoing, and that is that we're now capable of taking all human knowledge and converting it into sequences of ones and zeros. That's kind of an amazing thing. So by the end of this lecture, you'll see, well, how do we do that? You'll be able to answer that, okay? And there's one other thing, and this is actually going to be like most of the problems that we're going to do on this section. I do expect you to know the information, but we're going to do word problems with this, and we're going to be able to actually measure the sizes of particular things. Like I can show you a picture and you'll be able to say how big is that picture, and you'll have an understanding of what that means. Okay, now you already kind of know about these numbers because if you went out and bought a USB drive, okay, you would see something like on the side of it, it would say like 64 gigabytes, okay, which is kind of small these days, or 128 gigabytes, and you go, well, what is 128 gigabytes? What does that mean? It's actually a very exact measure of how much information you can put on that USB drive, okay? And so not only can we reduce all information to just a sequence of ones and zeros, okay, binary, but we can also measure it now, and we can accurately measure it. And it's just like you can measure in physics, you can measure like, the length of a table using a ruler, or you can measure time with a clock, or you can measure mass with a balance. Now in computer science, we can actually measure information, okay, and give it a very precise number. Okay, so let's start with that. All right, so how does encoding work? Okay, well, before I jump in and show you some encodings, I got to give you a little bit of an idea of how language works, like human language, okay? And this is a representational theory of language, okay? And what that means is that basically we have words, okay, like the word tree, okay? In fact, I should probably put tree in quotes here. So, if you hear me say the word tree, this picture should pop up into your head because you're an English speaker. And as an English speaker, you know that tree represents, this thing with like leaves, and looks a little bit like this picture right here that I have. Okay, this kind of stick drawing of a tree here. Okay, and so the word tree is the one side of this picture. The word is called the signifier. Okay, it's the thing that points to the signified, the idea or the tree, okay, like that. All right, and so in English, we have a signifier for a tree, and it is the sound tree, okay, like that. But there are other languages, okay, and like if you spoke Italian, the word for a tree is arbore. Okay, so if you said arbore, you would have this picture of a tree appear in your head. Now, if you didn't speak Italian and all you spoke was English and you heard arbore, it would just sound like gibberish to you. Like you would go, well, what does that mean? Okay, and in another language, like let's take some more a little bit different. This is the word for a tree in Hebrew. Okay, and it's pronounced etz. Okay, so a tree is etz. Now, if you didn't know Hebrew, again, that picture would not come up into your head. You go, well, what's etz? But if you were a Hebrew speaker, you go, oh, it's a tree. Okay, and I don't know Chinese. Okay, so I don't even know what those symbols mean. I just put it into Google Translate, but those are the symbols, and there would be some sound associated with that represents the Chinese word for a tree, and so on. Okay, Now, the reason I'm pointing out all these different languages is because this gives rise to this idea of a standard, okay? And so a standard is basically, it's kind of like a human language. And, just like with a human language, you can make a dictionary. Okay. Now, usually dictionaries are like one word defined in terms of other words, but you can imagine a dictionary in which you have like the word tree, and then beside it you have the picture of a tree so that you can see what it is that it's representing. Okay. Or you could have, like, I don't know, grass, and then beside that a picture of a grass and something like that. Okay. Now, if you had that kind of a dictionary and someone heard me say the word tree and they looked it up and they go, oh, it's that thing there, call it this thing. Or you heard grass, and then you could look up in the dictionary, you see the picture of the grass, and the person would know what I mean. Okay, so it's kind of like that with binary representation. What we're going to do is we're going to simply say, okay, what is it that we want to represent? What is this signified? Okay, in a human language, it's like the tree itself. Okay, and the signifier is the sound tree. Okay, so in computers, we want to represent, say, the letter R. Okay, and you say, well, how do I want to represent it? Well, computers only work in ones and zeros, so the letter R is going to be a sequence of ones and zeros. Okay, and maybe we want to represent the letter A. So here there's a letter A. Well, somewhere inside the computer, they can't work directly with A, it can only work with ones and zeros. Why? Why can it only work with ones and zeros? Because everything is made out of transistors. Okay, everything is made out of those silicon wafers with little transistors on them that are either on or off, on or off, on or off. Okay, and so if this computer is going to be working with this letter A, at some point it's got to turn it into a sequence of on, off, on, off, on, off, or ones and zeros. Okay, so there's this kind of a dictionary where a certain sequence of ones and zeros represents the letter A. Okay, another sequence of ones and zeros that represents the letter B. Another sequence of ones and zeros represents the letter C, and so on. Okay, and that's how we're going to do it. We're going to basically create this dictionary, which is a representation of all the things that we want to, all the information that we want to represent with the computer. And on the one side, it's got to be in the language of the dictionary. In the language of the computer. So one side of the dictionary, it's the language of the computer, which is ones and zeros, and the other side, in the other column, it's going to be the thing that it represents. Okay, so you got that idea. Now, a standard is a particular way of doing that. So just like there are different human languages, so there are different ways of, say, representing a tree. In English, it's tree. In Italian, it's arbore. In Hebrew, it's etz, and so on. Okay, so just like there's different ways of representing a tree, there are different ways of representing, say, the letter A in computers, because after all, the sequence of ones and zeros that represents an A, someone has to decide on that, and that arbitrariness means that one person might decide one thing and another person might decide something else. Okay, now if you did that, if everyone, if every computer decided, that a different sequence would represent an A and a different sequence in a different computer would represent an A, well, then you couldn't exchange information between the computers and expect that both computers would represent an A. Okay, and so what computer science has, the whole computer industry has, is a bunch of standards. Okay, and it's like these standards are kind of like, this is our dictionary for converting ones and zeros into English letters. Period. Everyone's going to use this dictionary. If anyone doesn't use this dictionary and decides to go on their own, well, then they're going to build a computer that is not operative. It doesn't have interoperability with other computers. Okay, because what looks like an A on one computer won't look like an A on the other one, because the same sequence of ones and zeros would be interpreted differently. All right, so that's what a standard is. Basically, it's a convention for mapping binary numbers to data items, to the data items they represent. Okay, and so this mapping, that's basically the idea of a dictionary. So like in one column you've got the ones and zeros, and in the other column you've got the data items that they represent. Okay, so there you go. All right, and nowadays we're going to look at a few types of encodings, and go like for two different types of encodings for letters. We're going to look at encodings for colors and so on. Okay, but if you go way back into the early days, there were actually two ways of encoding English letters. Two ways of encoding, and that caused a problem, because if you used a computer that worked with one standard called ASCII, and you took files that were like that were created on an ASCII computer, and you brought them to a computer that worked with Encoding, and that's right here, okay, Encoding, like that, the files wouldn't work, okay? And that's because what looked like an A on one computer did not look like an A on another computer, okay? Nowadays, and we're going to look a little bit at ASCII in a second, but nowadays, this sequence of ones and zeros, so that's 0, 1, 0, 0, 0, 0, 0, 1, that means the letter capital A, okay? So every computer in the world today that sees this particular sequence of ones and zeros will say, oh, I'm supposed to draw the letter A, okay? And if it sees this other sequence of ones and zeros, this one here, okay, so 0, 1, 0, 0, 0, 0, 1, 0, then every computer in the world says, oh, I'm supposed to draw the letter capital B, and so on, okay? And so, you know, these sequence of ones and zeros get mapped or converted or interpreted as the letter capital A or the letter capital B, and so on, okay? In Encoding, I don't even know what it was. I mean, I guess I could have looked it up, but this particular sequence was not converted into the letter capital A. It was converted into something else. And so you can see how that would cause a problem, because on ASCII computers, it would be the capital A, which is probably what you wanted, and then on other computers, it would not. And so these computers use two different standards. It's like they were talking two different languages, okay? And, you know, nowadays, Encoding is gone. Encoding was actually created by IBM, okay? And it's a silly name, okay? It actually is pronounced that way, Encoding. You know, it just, you know, kind of went out of use, okay? And, you know, like, it's kind of like, you know, if you look at all old technologies, once upon a time there were VHS tapes, cassette tapes, and then there was another standard called Beta, and Beta went out of, you know, kind of lost to VHS. But then VHS went out, and then that was replaced with CDs and DVDs, and CDs and DVDs are going out because everything's done, you know, like through Netflix or whatever. You don't go to Blockbusters to rent a DVD player. And so these standards, they're created, they're eliminated, and one standard will beat out another standard, and so on. But ASCII has been around for a long time, okay, and that's basically the standard by which English letters are encoded, okay? Now, before I jump into these encodings, I really want to get at this idea of, like, you know, being able to measure how much information is you know, in a single letter, okay? So you know like the saying, a picture is worth 1,000 words. It's kind of like saying, you know, because there's a lot of information packed into a picture. Can we make things like that precise? Can we precisely say, like, here I have the letter capital A highlighted. Could I say how much information is there in a single letter A? Single letter A, how much information is packed in it? And then beside it is this letter S here, like that. And it's like, how much information is in that S? And how much information is in that C? And if we added up the information in the A, and the information in the S, and the information in the C, we would have all the information in those three letters, and so on. In other words, could we have a precise measure of how much information is in each English letter? And the answer is yes. Okay. Now, how that works, let me just do it by pretending to create an encoding from scratch, okay? So what I'm going to show you right now isn't ASCII. In fact, I don't know anyone in the world that uses it. We're just going to pretend that, you know, we're computer science people, and like back in, I guess, the 50s, and we're going to come up with our own standard for English letters. And you say, well, how would we do that? Well, the first thing is we have to do is we have to say, well, how many things are we going to encode? Okay, so like how many different symbols are we going to encode? Characters. They're called characters, actually. Okay, and you go, well, okay, well, so we're going to stick to just English right now. Never mind, you know, French and Italian, or, you know, like Russian, which has different letters, or Hebrew, which has different letters, or Chinese, which doesn't even have letters. They have logograms. Okay, and you say, well, just stick to English right now. In English, we have 26 lowercase letters. Okay, so we have to be able to at least represent 26 letters. Okay, but you can't really write English with just lowercase letters. I mean, maybe if you're texting, but that's not really English. You know, you need uppercase letters for English, okay? So in addition to the 26 lowercase letters, you're also going to need 26 uppercase letters, okay? So far, we have 52 data items that we want to represent. A data item is just like an item, of data. Okay, so like the letter capital A is one data item, the letter capital B is another data item, and so on. Okay, so for the lowercase letters, we have 26 data items. For the uppercase letters, we have another 26. Well, that's still not good enough because when we write English, we have to put spaces between words. Okay, some ancient writing systems, they just stuck the words right up against one another. I don't know how they read that, but that's the way they did it. But in English, you need what are called white spaces. Okay, and that means just like spaces between things. Okay, and so like the space key on your keyboard is one of these, but so is the tab. Okay, and it's not just the tab, there's also the new line character. Okay, and there's a whole bunch of these are just basically things that space out the words so they're not all stuck together. Now, I don't know how many of them there really are. I'm just going to say 10, just for the sake of argument. It's not that important because this isn't a real encoding anyhow. We're just pretending like we're creating an encoding for academic reasons, okay? And then that's still not good enough because we're going to need punctuation, okay? We're going to need things like, you can't write English by just spacing out words. You need periods, you need commas, you need quotation marks, and things like that. Okay, so actually let me put in here a period, comma, quotes, etc. Okay, without those you're really not able to write good English. Okay, and we're still not done. We're also going to need the digital characters. I said 10 punctuation marks. Okay, the digital characters, and don't think of these as numbers, just think of them as the digits, as if they were letters. Okay, so if I were to write the number 365, I'd have to write the symbol 3 and the symbol 6 and the symbol 5, not the value 365, just the symbol 3, 5, or 3, 6, and 5. Okay, and we need 10 of those, right? 0, we need the symbol 0, we need the symbol 1, and so on. And I think for English we need that too. But we also then need some special characters, and again I said about 10 things like the tilde. The number sign, okay, dollar sign, percent sign, things like that, okay. And so, there's a bunch of different data items that we want to represent. If you add these all up, that adds up to 92 characters, okay. And so I said, look, we need an encoding that can cover 92 characters, all right. And so we're making that dictionary that I mentioned. On the one side, we have the binary numbers, and on the other side, we have the thing that they represent. Okay. Now, you might say, well, how long do my binary words have to be, okay, to represent 92 different characters? Okay. So, like on the one side of the dictionary, I have 92 different things to represent. And I say to myself, well, you know what? I'm going to try to do it with just 2 bits. And I think most of you realize you can't do it with 2 bits. But let me just say I'm going to cover all 92 possibilities with just 2 bits. So what that means is all my words are just 2 bits in size, 2 bits wide. Okay? And you can't. Because with 2 bits here, okay? With 2 bits, you can only cover 4 possibilities. And you go, well, why? Well, here's the dictionary. Okay, so on the left hand column right there, that BN, that just stands for the binary number. Okay, so that's what the computer would, because computers only work in binary, that's the word the computer understands. And that's going to translate into or map to the data item. Okay, now why do we have only 4 possibilities? Well, because let's go through them. Remember, you're only allowed to work with 2 bits. That's 2 binary digits. So one possibility would be 0, 0. Another one would be 0, 1. Another one would be 1, 0, and then 1, 1. That's it. There's no more possibilities, right? So if you go through all the possibilities with just 2 bits, you only have 4 entries into your dictionary. Again, 2 bits, there they are, the first one and the second one. And what are the 4 possibilities? 0, 0, 0, 1, whoops. 0, 0, 0, 1, 1, 0, and 1, 1 like that. And you go, okay, well, I've got 4 entries in my dictionary. And you go, let me start to fill them in. So here are the data items. These are the things that are being represented. Okay, so here's the A, here's the B, here's the C, here's the D, and then you've run out of entries in your dictionary. Okay, to use the language from above, this is like the signifier. And this over here would be the signified. Okay, just if you want to use the same language. Whoops, let me just put some round brackets around this here like that. Okay, and that's the signifier. So that's the word the computer understands, and this is how it interprets it. Okay, it interprets it as either the letter A, B, C, or D. Okay, but again, 2 bits, and you can only get as far as 4 entries. Okay, we say, all right, well, fine. Let me try to do it with 3 bits. But if you try to do it with 3 bits, it turns out that you have only 8 possibilities. And you say, well, how does 8 possibilities come out of 3? Okay, and here's why. Okay, because here's the dictionary. All right, with 3 bits, your first bit can be either a 0 or 1, your second bit can be either a 0 or 1, and your third bit can be either a 0 or 1. So there's 2 possibilities for the first one, multiplied by 2 possibilities for the second one, multiplied by 2 possibilities for the third one, for a total of 8 possibilities. Do you remember the example for the logical circuit where we had 3 switches, and I said there were 8 possibilities? Because the first switch could be in 1 of 2 positions, the second switch could be in 1 of 2 positions, and the third switch could be in 1 of 2 positions. So the total possibilities was 2 times 2 times 2. It's the same thing here. Okay, so if we went through all 8 possibilities, your first one would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. And that's it. There are no more possibilities. And you say, well, how many entries do I get with 3 bits? And you count them up. It turns out to be 8. Okay, and is that enough? No, we need to do 92, and we've only got 8. Okay, so if we started to fill in our dictionary here, we'd have the A, and then B for the second one, and then C, then D, then E, then F, G, and by the time we got to H, we'd run out. Okay, we run out of entries in our dictionary. Okay, so with 3 bits, you can only encode 8 data items, so that's not enough. So, okay, well, what about 4 bits? Well, with 4 bits, if you did the analysis, it turned out to be 16 possibilities. Okay, say, all right, fine. What about 5 bits? With 5 bits, you'd have 32 possibilities. Okay, that's still not enough because you need to get to 92. Say, all right, fine. Let me do 6 bits. And at 6 bits, you're still not enough. But at 7 bits, you reach 128. And with 128, will that cover 92? Yes. Okay? And so this is actually a measure of how much information is in one English letter. And you go, what do you mean? How do I know that? What do you mean it's how much information? Because if you said an English letter has 6 bits of information in it, that wouldn't be enough. Because with 6 bits, you'd only have 64 possible letters. Okay, or it's not just letters. I should say characters, because you got to include those other characters as well. So if you're saying, look, I just need to write English, and you go, well, English writing, every character in English writing is 6 bits in size, that would be too small. Okay, and then you go, well, is it 7 bits? And 7 bits is a little bit too big. So it's between 6 and 7. You can't have a fraction of a bit, so you need 7. Okay, and actually this is just like using a ruler when you're measuring the side of a table. Suppose you've got a ruler, and let's do it in inches because everyone's familiar with inches. Okay, so you put the 0 on the one side of the table, and then you go 2, 3, 4, 5, 6. Suppose you get to 6 inches, and the table is still a little bit longer than that. And you get to 7 inches, and 7 is too much, is a little bit further. It's between 6 and 7. There you go. You've just measured the size of a table. That's effectively what we've done to measure the size of information, okay, in a letter. Okay, so once again, what we did was we said, look, we need to encode 92 characters, okay, including those special characters, white spaces, and so on. And we said, well, for 92 characters, 6 bits is not enough. Okay, 6 bits is not enough. So is 7 bits enough? Yes. And so basically, at 7 bits, you have enough to cover 128 possibilities, which covers your 92, okay? And that basically sets the minimum size to how many bits are needed to encode English text. Each character in English text has to be 7 bits in size, okay? And there you go. That's how information is measured, okay? Now, I don't want to go off into other disciplines, but there's an equivalent of this in physics and in chemistry and biology. There it's usually called entropy, but it's the exact same idea, okay? And so when you're looking at a number like, on that USB drive and it says 64 gigabytes, that's a precise measurement of how much information you can put on that USB drive. Like I said, by the end of this lecture, you'll understand what that what that number means. Okay. All right. So let's go on. Okay. Now, oh, I already mentioned this. So what can we measure in the universe? Okay. What are the fundamental measurements? Length with a ruler, time with a clock, mass using a balance, like a scale. Okay. You might have done this in chemistry classes. And the fourth one now that we get out of computer science is information. Okay. All right. So the more information it requires, the more bits. Sorry, I should say the more bits that are required to encode something, the more information is in each data item. All right. And so there's your measure. Okay. Now, last thing before we actually start doing some very simple problems with this, let me just mention that when they actually started building computers, and they came up with this 7 bits to encode English. It turns out that building computers with buses that are 7 bits wide is really ugly. Okay, it's just an engineering thing. Okay, and so they actually extended the ASCII to what's called extended ASCII. So ASCII, the old ASCII, is technically only 7 bits. Okay, and that's all you really need to encode English text. But they extended it to 8 bits per character, and the reason they did that is just because it's easier to build computers with 8-bit buses rather than 7-bit buses. As you can imagine, everything with computers is power of 2s, and 7 is not a power of 2, but 8 is. Okay, and so it just turned out to be much easier to build things with in terms of 8 bits instead of 7. And so the ASCII code actually got extended to what's called the extended ASCII code, and the extended ASCII code is actually 8 bits per character, and that allows you to encode 256 characters. Okay, now there's a website called ASCIIcode.com, and that's actually where the ASCII code is. So let's take a look at that. Okay, let's take a look at some ASCII characters, and where is that? There it is. Okay, so here's ASCIIcode.com. All right, let me accept. All right, and here it is. Here's the ASCII code. So what you're seeing there is several columns. So one column is just decimal numbers, and then the other one is octal and hexadecimal. I mentioned them earlier, but take a look at the binary here. Okay, so like binary numbers like that. Okay, so that binary number, this is the dictionary that I've been talking about. That binary number, it's 8 bits wide. 8 bits of zeros, okay, so 8 zeros in a row, is basically what's called in ASCII the null character, and it just means do nothing. Okay, most of these encodings have a do nothing. Okay, and now there's a whole bunch of them, and I'm going to skip them. These are kind of like the white characters here. All right, like that. So these are the white space characters, which basically are like they're just like spaces and backspaces and tabs and so on. So let's skip those. Okay, and let's get to, where are they here? Here we go. Okay, so this particular sequence here. Okay, so let me see if I can make that a little bigger for you. Okay, how's that look? Good. That's a lot better. Okay, so 0, 0, 1, 0, 0, 0, 0, 0. That's basically a space. Okay, that's a space. The 0, 0, 1, 0, 0, 0, 0, 1, that's an exclamation mark. There it is, like that. Okay, and then the next one is a quote. Then the next one is the pound sign or the number sign. Then the next one is the dollar sign. Then the next one is the percent sign, and so on. Okay, again, when the computer, because the computer only works in ones and zeros, whenever it sees that sequence of ones and zeros in a file, it goes, oh, I'm supposed to draw this thing. Now we know that as the percent sign, but the computer just says, oh, I'm supposed to draw that because I encountered that sequence of ones and zeros. Okay, so just like in a human language, this is the word, the signifier, and this is the signified. Okay, and so let's just scroll through these because it's not important that you know the ASCII code in detail, just that it exists. Okay, so like here, if a computer wants to draw the number 1, remember this is not the value 1, but it just wants to draw a 1 as kind of a letter. Okay, then internally it would have that sequence of ones and zeros, 0, 0, 1, 1, 0, 0, 0, 1. Computer encounters that sequence, it draws this. Okay, and all right, so there are all the digits. Okay, colon, I guess I forgot these, like, less than, equal sign, at. And here we go. Here's the letter capital A. Okay, so there's the sequence of ones and zeros that gets mapped onto the letter capital A. And then, the next one is the letter capital B, C, all the way up to the letter Z. There. Okay, so this sequence of ones and zeros gets mapped to that. All right, and then there's some more special characters here, some brackets, backspace, the caret, underscore, backtick, and then we get to that one, and that one 0110001 is the letter A, lowercase a, and so on. All right, and let's finish them off. At this point, we've gone through the old ASCII code, which was just 7 bits. With 7 bits, the highest you can count is from 0 to 127. Okay, that's 128 possibilities. And the reason you only get to 127 is because your first possibility is 0 itself. Okay, so from 0 to 127 is 128 possibilities. Okay, but because this is the extended ASCII code, notice that the first digit was 0 for all of them. Going on to the extended ASCII code, okay, there it is. The next one, they had to pick a symbol. They decided that that's the euro symbol, okay, and so on. And so you can see that, they just, again, this extra bit there that was added, the leftmost bit, it was added simply because it's just annoying to build computers with 7 bits. It's easier to build them with 8 bits. And so they extended it to 8 bits. Okay, and you can see here there's some more symbols that they added. Like the cent. And this is the pound sign, like British pounds. I think this is yen. This is the paragraph separator, the copyright symbol. This is an upper script A, okay, like a superscript. Registered trademark. There's mu that we saw earlier, okay, and so on, okay. Don't have to go through all of them. All right. And there we go. That's the extended ASCII code. Okay, great. So let's think about expanding this to other encodings, because we're going to be doing that in a minute. So with English text, okay, we said we had to encode at least 92 characters. And so with 92 characters, you needed 7 bits per character. Every character has to be 7 bits. You might ask, well, how many data items can you encode with a given number of bits? Okay, and that's what this table is all about. In fact, here I should probably say data items just to be complete here, like that. Okay, so number of bits here, and then the number of data items that you can code there. Okay, so if you've got just 1 bit, okay, well, how much can you encode with 1 bit? That's pretty easy. There's only 2 possibilities, 0 or 1. Okay, so with 1 bit, you can only encode 2 different things. Okay, with 2 bits, we saw this already. You can encode 4 things. You can encode 4 items with 2 bits. You might say, well, what would that be good for? Like, what is something that has only 4 data items in it? DNA. So DNA, I forget what the letters are, but there's guanine. I don't know. I don't know my biology, but there's 4 different nucleotides for DNA. So if you wanted to do like your DNA sequence, the first nucleotide, there'd be 4 possibilities. You just need 2 bits for that one. Your second nucleotide would need another 2 bits. Your third nucleotide would need another 2 bits. Each nucleotide in your DNA sequence would require 2 bits. Okay, so that would be called a 2-bit encoding. So DNA is a 2-bit encoding. Okay, with 3 bits, we saw that it was 8. With 4, it's 16. With 5, you can do 32. With 6, 64. With 7 bits, you can do 128. With 8 bits, you're at 256. This is your extended ASCII code. With 9 bits, it's 512. And with 10 bits, you're up at 1024. Okay, now, in general, if you have n bits, okay, so now I've just generalized it to n, the number there would be 2 to the power n. Okay, so what does that 2 to the power n mean? It means if you have n, you just take 2 and you multiply it by itself n times. Okay, so here, this is actually that 10 to the 24. That's actually equal to, that 1024, that's actually equal to 2 to the exponent 10. Okay, so make sure you know how to do exponentiation on your calculator. If you take 2 and you multiply it by itself 10 times, so 2 times 2 times 2 times 2, 10 times, you're going to get 1024. Okay, so with n bits, you can encode 2 to the n data items. All right, so there you go. Okay, now all of this is like very old stuff with computers. And so what happened is because everything was being grouped into bundles of 8, okay, with the ASCII code, everything was ASCII in the early days. They gave 8 bits, a collection of 8 bits, they gave it a special name. 8 bits is what we call a byte. Okay, and now the language is starting to sound familiar because again, you go out and buy that USB drive, and on the side of it, it says 64 gigabytes. Okay, and so generally we don't talk about bits that much. We do when we're working with computers at kind of the microscopic level, but it turns out that it's easier to talk in terms of bundles of 8. Okay, so if you have 8 bits, that's a byte. If you have another 8 bits, that's another byte. Another 8 bits is another byte. Okay, the symbol for a bit is little b, and the symbol for a byte is a capital B. Okay, so just keep that in mind. And 8 bits is basically equal to 1 byte. All right, so 8 bits is equal to 1 byte. All right. When you go to measure the size of a file or something like that, we can talk in terms of bits, but even the size of the files, and we'll see that in a little bit when we look at the size of, say, an image, that'll turn out to be in bytes as well. Okay, so file sizes are in bytes and so on. It's almost never in bits. Okay, now the analogy you can take here, this is kind of a weak analogy, but just so you can kind of get your head around why they chose bytes instead of bits, is like imagine if you had like eggs. Okay, when you go buy eggs, you buy like a dozen eggs. To say, look, I want a dozen eggs, or to say I want 12 eggs, is to say the exact same thing. Okay, say, look, how much does 12 eggs cost? How much does a dozen eggs cost? It means the same, because a dozen is 12. Okay, and it's the same thing with between bits and bytes. Okay, if I say 1 byte of information, that's the same as saying 8 bits of information. Okay, a byte is 8 bits. All right. Now, how does this work though when you start to get beyond just a single letter? So if you have a single letter, each ASCII letter is an extended ASCII is 8 bits. So you got one letter, that's 8 bits. You've got another letter, that's another 8 bits. You've got another letter, that's another 8 bits. So if you've got like 3 letters here, so I could ask the question, how many bits does it take to encode the following? Okay, or how many bits does the following take to encode? All right. And I asked you to answer in both bits and bytes. So I say here, okay, we want to encode the word cat. How does that work? Well, we have to encode first the letter C, and that C takes 8 bits. But then that A there, we also have to encode the A. That's another 8 bits. And then the T there, that's another 8 bits. Okay, and so if you have 8 plus 8 plus 8, each character is 8 bits. That's a total of 24 bits. Okay, so make sure you understand that each letter has to have 8 bits. You've got 3 letters, so you have to have 3 times 8 for a total of 24 bits. Okay, but 8 bits is a byte, so that's the same as 24 bits is the same as 3 bytes. Okay, so in answer to the question, how many bits does it take to encode cat? 24 bits. Okay, equivalently, how many bytes does it take to encode cat? And the answer is 3 bytes. Okay, I think you can already see that why bytes are kind of convenient, because each ASCII letter is 1 byte. So if you say here, well, okay, how many bytes does it take to encode cat? How many letters are there? 1, 2, 3. 3 letters, 3 bytes. All right. Okay, what about this one? How many bits does it take to encode that? Hi there, period. Because you got to be careful, because ASCII doesn't just include the letters. That's why I tend to say characters. Okay, it also includes the white space in there. That's this piece right here. Okay, so you have to have a space between the words. Otherwise, if you stick them together, I mean, maybe you'd be able to interpret it, like if I had that. But could you imagine reading text like that? That would be impossible if all the words were stuck together. Okay, and so high there is like 1, 2, 3, 4, 5, 6, 7, 8, and then the period is also a character, so that's a total of 9 characters. Okay, each character is 8 bits, so 9 times 2 is a total of 72 bits, or 9 bytes. Okay, so if you've got 9 characters, that's 9 bytes. All right, 9 characters ASCII. 9 characters ASCII is 9 bytes. Okay, what about this sentence? The brown cow jumped over the full moon. Okay, well, if you just counted the number of characters there, and I did, that's 40 characters. 40 characters is going to be 40 bytes. Okay, each character is encoded by 1 byte. It requires 1 byte to encode it, and so that's 40 bytes. But then, if you want that in bits, multiply it by 8, and there you go. Okay, so that would be what it is in bits. All right. So just multiply it by 8. Okay, so so in this next little piece here, just to give you an idea, this is just an example. In fact, I should probably just say example here. There we go. Okay, like example. If a file had, actually, I should say it right here. Example. Okay. So if a file had like 2,250 characters in it, including the white spaces, the punctuation, all those sorts of things. Okay, if it had 2,250 characters in it, then the size of that file, okay, would be 2,250 bytes. Okay, so that's the way that that works. Okay, so it was kind of convenient in the early days to work in bytes, because if you say how many bytes are in the file, 2,250, that would tell you exactly how many characters there were in the file. All right, now before we look at the other encodings, let me just start to tell you, because we're going to be doing word problems with these, let me just tell you that these numbers get big very fast. Okay, and so another thing that you need to know is not just bits and bytes, okay, but also like kilobytes and megabytes and gigabytes and terabytes and petabytes. Okay, in other words, there's a metric prefix that you can put in front of the bytes, because if we're going to say like 1,000,000 bytes, you can say 1,000,000 bytes, but no one ever says that, especially if the numbers get big, billion bytes, trillion bytes, and so on. Instead, if you have 1,000,000 bytes, you just say megabyte, okay, and you write it as capital MB. So you're going to have to know also these metric prefixes, okay. And so 1 kilobyte, okay, in most sciences, except for computer science, okay, kilo means 1,000. Okay, so for instance, if you're in physics, if you say a meter, that's like 3 feet, a meter. If you have 1,000 meters, that's a kilometer, a kilometer. Okay, but in computers, it's a little different. These metric prefixes work a little different. Because everything in computers is in powers of 2, they actually changed the definition of a kilo in computers. Okay, it's an approximation. So like in another science, kilo just means 1,000, but watch it in computers. If you say kilo, you actually mean 2 to the 10. Okay, and again, that's because everything in computers are binary and everything is in powers of 2. And so this is a slightly different definition. Okay, so when you say kilobyte in computers, that means something different than kilometers. In computer science, when you say kilobyte, you're saying 2 to the 10 bytes. 2 to the 10, if you take 2 and multiply it by itself 10 times, you're going to get 1,024, okay? Which is close to 1,000, but it's a little bit over. It's over by 24, okay? So in computers, kilo is actually defined as 2 to the 10, 1,024. Similarly, in other sciences, like physics, chemistry, and so on, mega is defined as 1,000,000, okay? And 1,000,000, of course, is a 1 followed by 6 zeros. But in computers, mega is defined as 2 to the 20. All right. Now, 2 to the 20 means 2 multiplied by itself 20 times. It's close to 1,000,000, but it's a little bit over. There it is. That's what it's actually equal to. So it's 1,000,000, but it is over by 48,576. And you say, well, that's a lot. Yeah, but not, compared to 1,000,000. Okay. So it's like a 4% error, or actually more like a 5% error. 4.8% error. Okay, and so yeah, it is off, but it's close. Okay, and because you have to really work in powers of 2 in computers, they said, you know what, we're just going to define mega as being 2 to the 20 when we're talking about computers. So when it comes to computers and you say a megabyte, you really don't mean 1,000,000 bytes, even though we'll make that approximation later because it makes the math easier. technically speaking, when you say a megabyte, you're really saying 1,048,576 bytes. Okay? And again, that's just because everything in computers is in powers of 2. All right? Now, here's a table for all the metric prefixes that you're going to need in this course. Okay? And I don't know if you'll need anything bigger than peta in your lifetime, but you might. Okay? Depending on how big information gets in the future. And so let's go through each of the lines here. Okay? So kilo, all right? Kilo here is in computers is 2 to the 10, and that's 1,024. Okay, that is approximately, that little tilde there means approximately. That's approximately 10 to the third power, means 10 times itself 3 times, and 10 times 10 times 10 is 1,000. Okay, so kilo is technically in computers 1,024. We will, when we do these word problems, approximate it to 1,000. Okay, mega is, when it comes to computers, is 2 to the 20, okay, which is like 1,048,576. That is close to 10 to the 6th power. That's like 10 multiplied by itself 6 times, which is close to a million. Okay, and so mega, we'll approximate it as a million when we do our word problems, but it is technically exactly 2 to the 20. And you should know that. You should know that there's an exact number and then there's the approximation that most people use. Okay, people know this difference. When people do calculations, they'll calculate it based on like 1,000, million, billion, and so on. But technically speaking, that is the exact answer. So giga is 2 to the 30th power, which is a little over a billion. Okay, tera is 2 to the 40th power, which is a bit over a trillion. Peta is 2 to the 50th power. I don't even know if there's a word for that in English. But there you go. Okay, now you can notice a pattern here. 2 to the 10, kilo. 2 to the 20 is mega. 2 to the 30 is tera. 2 to the 40 is tera. Oh, I think I said it wrong. So 2 to the 10 is kilo. 2 to the 20 is mega. 2 to the 30 is giga. 2 to the 40 is tera. 2 to the 50 is peta. Okay, so it goes up by powers of 10. Each metric prefix goes up by powers of 10. Okay, 2 to the 10. Okay, all right. Now, sometimes these things are called binary prefixes to distinguish them from metric prefixes. Okay, so the metric prefixes are like the 1,000, million, billion, trillion, and so on. And the binary prefixes are like the 2 to the 10, 2 to the 20, 2 to the 30, and so on. Okay, and people even tried to change the names to distinguish the two. So we'd use kilo in the metric system, and they tried to get people to say kibi for binary prefixes, and mebi instead of mega, and gibi instead of giga, and tebi instead of tera, and pebi instead of peta. But you know what? It just didn't catch on. Okay, so I mentioned this only in passing because there were people that said we really want to make this distinction, so we don't want to say kilobyte, we want to say kibibyte, but no one does that. Okay, so I just mentioned it here because there is a difference, but everyone just defaults over to thinking of kilo, even though it's technically that, they default over to thinking of it as 1,000 and so on. Okay, now if you want to see these, I won't bring them up on the web page right now, but if you want more information about this, you could just go to the Wikipedia page on binary prefixes and metric prefixes, and you won't need anything except for what I gave you here for this course. In other words, you'll only need this chart here. Okay, but I do want to mention those other wiki pages because in other courses you may need them. Okay, and they have, those wiki pages have everything. Okay, whereas here I just have the bare minimum of what you need for this course. The wiki pages have like everything. Okay, so that's why I mentioned them in passing. Okay, all right, now we're going to use these to do word problems, but I'll do that later. Now, let me show you other encodings, okay? So what do I mean by that? Well, we've looked at one. So one encoding is, how do you encode, how do you render as a sequence of ones and zeros English text? And the answer was the ASCII code, okay? technically the extended ASCII code, okay, because the old ASCII code, in fact, I could probably just say here old ASCII was 7 bits wide, okay, and the extended ASCII turned out to be 8 bits, okay, and we already studied that in detail, so there's no reason to study that anymore, okay. Another encoding that came after ASCII was Unicode, okay. Now, what is Unicode? So, if you want to represent, say, French or German, even though German is written like with English like letters, there are some German letters that are not in the English alphabet. Okay, so there's one of them that looks kind of like a B. I don't know if anyone knows German, but there's one of them that looks like a B. Or there's also just like like the letter U with 2 dots on top. Okay, and that's not in the ASCII code. Okay, and so people said, well, you know what, we need more than just ASCII. So they kept expanding and expanding it. And finally, they came up with what was called Unicode. Now, Unicode is actually a huge encoding. All right. Each Unicode character is 4 bytes. Okay. So let's be clear what we mean by that. So in ASCII, one ASCII character was 1 byte. Okay. But in Unicode, one Unicode character is actually 4 bytes. 4 bytes is the same as 32 bits, okay? And you say, oh, that's a lot more. All right, so talking in terms of bits, with ASCII, one ASCII character was 8 bits, but one Unicode character is 32 bits. And you might say, well, how much could I encode with 32 bits? And the answer is over 4 billion possibilities. Okay, so there's 4 billion entries in the Unicode dictionary. Okay, and if you go back to that table where you say, well, how many things can you encode with 32 bits? 32 bits means that the encoding is 2 to the power 32, and 2 to the power 32 is 4 billion and extra. Okay, so it's a little over 4 billion. And you go, well, why would they ever need so many entries in a dictionary just to do, letters or alphabets? Okay, and the idea was to create one dictionary that would encompass all alphabets for all time. Okay, and so there's just no way that humans are ever going to develop so many different alphabet systems that we're going to need more than 4 billion entries. Okay, and so this was overkill on purpose, because what it basically meant is that what it means is that there's a lot of spaces in the Unicode dictionary that are not filled yet. And if you go out and you discover a new alphabet, okay, so how can you discover a new alphabet? Well, maybe you're an archaeologist and you're digging and you discover this new alphabet of some ancient civilization. Well, you can write to the email the Unicode Consortium. This is a group of companies that do Unicode. And you could say, look, we've discovered this new alphabet. Can we get Unicode encodings for this? Can we enter these into the dictionary? And there's a way of doing that. And then, yeah, they'll allow you to put in more entries into the Unicode dictionary. And that means that the dictionary, the number of entries doesn't increase. Okay, so there's always going to be 4 billion possible entries. I should say the number of possible entries doesn't increase, but the number of actual entries that can increase, because there are these huge blanks, okay, with 4 billion possibilities. So that means that not only are you encoding alphabets, like all European alphabets, but you're also encoding all Eastern alphabets, like Cyrillic, because like the Russian alphabet. You're encoding Semitic languages like Hebrew and Arabic, okay. You're encoding things that are not even alphabets, like Chinese. Chinese is not an alphabet. An alphabet, is usually like, like 20, 30 letters, okay, makes up an alphabet. But Chinese, each character is like a syllable, or like a word, or, maybe 2 characters are a word. And so you need about 2 to 3,000, you need to know about 2 to 3,000 characters before you can write Chinese properly. Okay, there's that many different characters. There's even more, but I think for basic Chinese, I think you need at least 2,000 characters. Those are all encoded in Unicode. Okay, and so like the sky's the limit. They even have ancient Egyptian encoded. They have uniform And believe it or not, this is just how geeky this world is. From Star Trek, the science fiction thing, there's the language Klingon, and there are all these fans of Star Trek, and they actually have a language called Klingon. It's not a real language; it's a made-up language, but it's got an alphabet that's even in there. Okay, so Unicode encodes a lot of things. It also encodes some like little tiny glyphs, like I don't know, like I think there's like images of like a tennis racket and things like that I've seen. So there's a lot of stuff encoded in Unicode. And you say, well, why is there so much encoded? Because there can be. Because with 4 bytes per character, you've got 4 billion possibilities. And with 4 billion possibilities, you've got, a huge dictionary. Okay, so that's the story with Unicode. And let me show you that. Okay, so where is that? So this is the Unicode home page. Okay, and it's a little bit busy, but let me just switch rather than navigating it. Here is the current Unicode encoding for Unicode 4.0. Oh, sorry, 14.0. Okay, so as they keep expanding the dictionary, they keep releasing new versions of the of Unicode. And here, just why not? I just chose Hebrew. Okay, so you can see here Hebrew, and so that word etz that I had earlier. The first letter was this letter here. It's ayin, and there's the encoding right there. So you're seeing 05E2, and you go, that doesn't look like binary. I know it's hex, but if you converted that hex into binary, it would turn out to be 32 bits wide. Okay, so in order to represent this letter here, you would need a unique sequence of 32 ones and zeros. Okay, and then the other letter was this letter here. It's the Sade. Well, it's called Sade Sofit. It's the letter that comes at the end of a word. Okay, and there's its encoding. Okay, and it is also 32 bits. Okay, so that's the encoding in hex. But in binary, it would be a sequence of 32 ones and zeros, and that unique sequence represents that particular letter. Okay, and I can just scroll through this, and I don't know. There's lots of different over here. So here's Greek. All right, so we'll just pick a few. Over on the side here, there's all the different languages. Okay, so there's Greek, there's Arabic right there. Okay, I don't know. I don't even know what language this is. Okay, here's Bengali. All right. I don't know. Here's Ethiopic. I mean, the sky's the limit. All right. So, here's Cyrillic, extended Cyrillic. That doesn't seem to be all of it, but that's just the extended part. Okay. All right. I'm not gonna go through all of it. Oh, arrows. Here we go. So, like I said earlier, there's other glyphs that are that are part of Unicode, and so they decided, why not encode arrows? Okay, so that's also in Unicode. Okay, enough of that. But it's important to understand that if you have a Unicode text, and say you have a word in Unicode and it's 3 characters long, okay, like cat, that first letter isn't just 1 byte, it's 4 bytes. So there's 4 bytes for the first character, 4 bytes for the second character, and 4 bytes for the third character, for a total of 4 plus 4 plus 4, or 12 bytes. Okay, and so 3 letters of Unicode are 12 bytes in size. Okay, so just keep that in mind. It's a different encoding, and different encodings could be of different sizes. All right, let's get to something more interesting, because both ASCII and Unicode are about writing. But let's go to something even more interesting. Like, how about color? You say, how in the world can you encode color? And it can be done. Okay, so how is color encoded? All right, so the way you do an encoding is you have to look at all the possibilities. Okay, now we're not going to encode any old color, because birds can see a lot more colors than we can, and we can see a lot more colors than dogs can. And so we don't have to encode all possible colors, because there's an infinity of possible colors. We only have to encode all possible humanly visible colors. And you say, well, how does that work? Well, the human eye has these cells in the back called cones. Well, they're also the rods, but the rods can only see black and white. Okay, but the cones see color, and there are three different cones. There are cones which are sensitive to red light, there are cones which are sensitive to green light, and there are cones which are sensitive to blue light. Okay, and those are the three primary colors. Now, I should say something about primary colors. Other people will define the primary colors differently. I'm talking about the primary colors the way the back of the human eye sees them. Okay, so if in our class they told you that yellow was a primary color, okay, but I don't want to get into all of the physics of color. Yeah, the physics of color. I just want to talk about encoding color the way the human eye sees it. So there are cones which are sensitive to red light. There are cones which are sensitive to green light, and there are cones which are sensitive to blue light. And so you say, well, how do I see yellow? Because I don't have yellow cones, and the answer is if your eyes are seeing a lot of red and they're seeing a lot of green, they perceive that, and very little blue. So, the red cones are firing off. They're saying, hey, I've got a lot of red stimulation. And the green cones are firing off. They go, hey, I've got a lot of green stimulation. And the blue cones are going, I've got nothing. You perceive that as yellow. So yellow is a secondary color, which is made up of the primary colors red and green. Okay? That's the first thing, that there's basically these three channels for color. All right? And all colors out there, all possible colors, are admixtures of these three channels, of the three primary colors. Okay? The other thing is, you might say, well, how many different levels can the human eye see? Like, how many different shades of red can you see? How many different shades of green can you see? And how many different shades of blue can you see? In other words, within each channel, how many different shades can you see? And this varies, and I'm going to say it's roughly around 200. Okay, you don't have to be exact. So you say to yourself, well, how many bits do you need to encode 200 different possibilities, 200 different levels? Okay. And by different levels, it means that, if I had like one shade here of red and another shade of red, which was slightly different, could you tell the difference between the two? If you can, those are two different levels. Okay, so there's about 200 different levels that you could see if you compare them side by side. Okay, and 200, you might say, well, how many bits do I need to encode 200 different levels? Well, if you had 7 bits, you could only do 128. We saw that earlier. With 8, you could do 256, and so there's your answer. Okay, you need at least 8 bits. All right, you need 8 bits for a total of 256 levels for red, say. And then you need the same, another 8 bits for green, and then another 8 bits for blue. So each of the channels, red, green, and blue, okay, 3 channels, for each of those 3 channels, you're going to need 8 bits for the red channel, 8 bits for the blue channel, 8 bits for the green channel. Okay, and so you might say, all right, well, how many possibilities is that? Well, there's 256 possible levels of red, multiplied by 256 possible levels of green, multiplied by 256 possible levels of blue. And if you multiply all that out together on your calculator, you will get 16 million different possible humanly visible colors. I think the number's somewhere more like 10 million, but it's okay. It's better to go a little bit over than under, okay? And so there you go. Each color is basically 8 plus 8 plus 8 bits, okay? 8 for the red, 8 for the green, and 8 for the blue, okay? And if you add 8 plus 8 plus 8, you get 24, all right? And so there's 24 bits for each humanly visible color. All right, so let me show you that. Let me demonstrate that for you using this website right here. And then I'm also going to show you how dogs see colors, because dogs apparently only have 2 cones. It's not that dogs are totally colorblind. They can see color. They just only have 2 cones instead of 3. Okay, and bees have 4. Okay, so they can see even more colors than we can. But, I can't show you that because you're only human. Okay, so you can only see as many colors as humans can see. Okay, but I can show you roughly what dogs see. All right, so let's take a look at that. All right, so here is a picture of the human eye. All right, and basically, if you look at the back of the eye, so this is the front of the eye, the lens here, where the front of your eye where your lens is. Okay, and then the image is focused onto the back, onto the retina. Okay, and if you expand the retina, which you're seeing here in this right here. Let's see if I can make that maybe a bit bigger for you. I don't think I can. Oh wait, there it goes. All right, how's that look? Yeah, a little bit better. Okay, so what you're seeing back here, whoops. Now it's scrolled down. Okay, what you're seeing back here is you're seeing that cell right there. That's a green cone. Okay, and they're the rods. Okay, but the rods, we're not that interested in them because they only see gray level. Okay, they only see black and white. Okay, so there's a green cone. So that's a cell which is sensitive to green colored light. There's a red cone which is sensitive to red light, and there's a blue cone. Okay, which is sensitive to blue light. Okay, so if you're seeing yellow, basically your red cones are being stimulated, your green cones are being stimulated, and your blue are not. Okay, and if you're seeing something like magenta, which looks like purple, well then your red cones are being stimulated, your blue cones are being stimulated, and your green ones aren't. Okay, and all different possibilities. Like you don't have to have pure magenta. So the green cones, they can see about 200 different levels of green. The red cones can see about 200 different levels of red, and the blue cones can see about 200 different levels of blue. And so you need 8 bits for your green, another 8 bits for your red, and another 8 bits for your blue, for a total of 24 bits to see all humanly visible color. Okay, so there's the human eye. Okay, and actually there's the picture already expanded. Okay, for dogs, you might say, well, how do dogs see the world? This is a bit of a guess. Okay, you can see that the kind of blue-green color of the wings here, they come across. Okay, but the yellow of the chest of the bird on the left here is kind of coming across as a kind of a greenish gray there, like that. So there's a little bit of color that dogs see because they've got two different cones. Okay, but generally speaking, it's a more subdued color. They don't see colors quite as vibrantly as we do. And of course, if you were a bee, you would see even more colors that we can't see, including colors in the ultraviolet, which is beyond our ability to see as humans. Okay, and there it is, expanded. So just to give you an idea of how this works in terms of like ones and zeros, I've got this web page here. This is a basically a color wheel here. Okay, let me expand that for you. See, does that look good? It does. So this is a color wheel. Okay, and there's a lot of stuff going on here. So let's just concentrate on this part right here where it says hex. Okay, now hexadecimal is used a lot, but I don't want to teach you hex. Okay, it's sufficient just to tell you that the first two digits there that are F there, okay, you see the two F's that are highlighted there, that's 1 byte. And that's the byte, that's in other words 8 bits. That's 8 bits or 1 byte. And those 8 bits there, they represent the the red level, okay? The next one is the green level. So those two zeros there represent how much green is in the picture, and there's no green. Okay, and then the last two, how much blue there is. Okay, so for instance, if I made all of them 0, then you have no red, no green, and no blue. You've got no color at all. That's black. Okay, if you've got F, and by the way, F is as big as you're going to get. Okay, so that basically says, actually let me make them capital. Okay, that basically says, okay, I've got no red. Okay, so there's no red. And FF is basically 255. It's maximum. Okay, it's like 8 ones in a row in binary. Okay, so this says I've got no red, I've got maximum green, and no blue. And then that's what you would see there. Okay, and then finally, we could go, okay, no red, no green, and maximum blue, like that. And there you go, you could see that it's blue. All right, now what if you had a little less than maximum? So FF is maximum. What if you had like 99? Well, you could see that this is a little bit of a darker blue, okay, because it's a different level. It's a darker blue. And what if I had I don't know, like 70 there? And you could see it's an even darker blue. Okay, and what if I had like 50 there, like that, 50, and that's even darker. Okay, what about 30? Okay, and now it's like a navy blue. It's a really dark blue. Okay, and then finally when I get to 0 there, like that, 0, 0, I'm back basically down to black. So what you're seeing is that you've got everything from no blue at all to maximum blue, like that. Okay, and so how many levels are there? There are 255 levels of blue. And how many levels of green are there? There's another 255 levels of green. And how many levels of red are there? There's 255 levels of red. Okay. And by the way, if you have maximum red plus maximum green plus maximum blue, you get white. Okay, and you can see in here that's white. Okay, but any color that's humanly perceivable, and I can just pick my color wheel here, and like I don't know, I could just type in some number there, like I don't know, like let me do 257A FF, like that, and you could see that this here, that's just a little bit of red, and then there's a little bit more green, and there's maximum blue, and you could see it's this color right there. Okay, and like literally any color that you can possibly imagine, okay, can be made that way. If I take away all my blue, I'm going to get something which is this kind of icky green there. Okay, kind of a olive green there, like that. Okay, and if I take away even all my red, it's going to be even greener. Okay, and so on. By the way, if I have lots of red and lots of green, whoops, one more, there we go, that's yellow. So if you take, you wouldn't have expected it, but if you take a lot of red and a lot of green and no blue, you get yellow. Okay, and that's a secondary color. Okay, and if you have no red and you have green and blue, you get what is that? Cyan. Okay, and if you have red and no green and blue, you get magenta. Okay, and cyan, magenta, and yellow are your secondary colors, and so on. And there's all the other possibilities in between. Okay, now we don't have to study all of this. It's sufficient to know that basically each of your channels has 8 bits, or in other words, it's 1 byte for each color channel. Okay, and so what you have for any particular color, to encode any particular color, is either you can think of it as 24 bits or 3 bytes. Okay, so maybe we could just summarize that here. Any perceivable human color, let's say it this way, any humanly perceivable color is 24 bits, which is the same as 3 bytes. Okay, I guess we're using little b's for bits. Let's do that like that, right there, like that, is equal to 3 bytes. Okay, and just to be very clear, one byte for your red level, another byte for your green level, and another byte for your blue level. All right, there you go. And that's how you can encode any old color. All right, now that we can encode any color, you might say, okay, great, how do I make a picture? And it's as simple as you might expect. That's what bitmaps are. Okay, so there are different ways of doing pictures, but basically bitmaps are just a grid of little squares, and I'll show you one in a second. Each little square is a color. Okay, and so by putting all these little squares all beside one another, you can paint a picture. Okay, each little square is called a pixel. Okay, and you might have heard that term, because if you buy a camera, you buy like one of those cameras, like they look like the old 35mm cameras. They're called SLR cameras, and you might read the box and it says 8 megapixels. Okay, it means 8 million pixels. It means each picture is made up of 8 million little squares. Okay, and each square is a pixel, and they form a grid. Okay, so let's take a look at that. All right, let's take a look at what a bitmap looks like, and let me switch here to this one right here. Okay, so this is a picture of our parking lot D. Parking sign. Okay, and you can't see the little squares because they are small enough that your eye just kind of blurs them together. Okay, but if we zoom in, all right, if we zoom in here, and I'm going to zoom in 4 times. Okay, what you're noticing is, I don't think I can zoom in anymore, but what you're noticing, maybe you could see it here on the windshield of the car, you can see how there are like these little squares. Okay, and so the whole picture is actually made up of a bunch of little squares. It's a grid, and there's all these little squares. And the reason they blend in together is because one square and its neighboring square are roughly the same color, but not always. They'll make a transition. So you'll see, like there'll be some, like over here, there's some, where my cursor is, there's some black squares, and then they transition into more gray squares and so on, okay? And so each one of those squares is called a pixel. Each pixel is one and only one color. Okay, so it's not like the top of the pixel is, say, a darker red than the bottom of the pixel. No, the whole pixel, the whole square is one and exactly one color. Okay, I wish I could zoom in more, but I can't with this particular program. But I don't know, you can see that, like where my cursor is, there's that one blue square there. It's kind of tiny, but that one square, it's all one color. Now, to encode a color takes 3 bytes. So each little square here, each little pixel is 3 bytes. Okay. Now, if you want to say how big is this file, you could go through it and you can say, okay, there's a pixel, that's 3 bytes. Here's another pixel, another 3 bytes. Here's another pixel, another 3 bytes. And if I add up 3 bytes for each pixel, what do I have? I have the total size of the file. Okay. Now, the file, I can actually measure it using the computer. Okay, so I'll show you how to do that at on a later class. Okay, but I basically said, how big is this file? It's called index.bmp. BMP is the extension that means bitmap, and the computer told me that it is a 149 kilobytes, like that, 149 kilobytes. Okay, now remember what kilo means. It means 1,000. All right, so this is actually, if you wanted to reduce it down to bytes, this would be 149,000 bytes, like that. Okay, so now what? Well, can we actually figure out, can we actually calculate how big that file, how big we'd expect that file to be? So there's another program I used. Again, I'm going to skip it for now. I can show you in a future video how I did this. But there's another program called GIMP, which is the photo editor. Okay, and I asked this photo editor, how big is this file? And remember, the bitmaps are like a grid. Okay, so they've got so many rows and so many columns. And the computer program told me, GIMP stands for I don't know, new image manipulation program. Okay, GIMP told me that the image was 333 columns. Okay, by 153 rows. Okay, so there were 330 columns of pixels and 153 rows of pixels. Okay, well, if you multiply them together, you multiply the number of columns by the number of rows, and you're going to get the total number of pixels. And the total number of pixels is 54,000. Let me put a comma in there so it's a little easier to read. Sorry, 50,490. So 50,490 pixels. Okay, that's how big that picture is in pixels. But remember, each pixel is exactly one color, and to encode a color you need 3 bytes. So each pixel is 3 bytes. Okay, so if you take the 50,490 and you multiply that by 3 bytes, because each pixel is a byte, you get 151,470 bytes, which turns out to be 151 kilobytes, which is a little bit different than the 149 bytes, but there's some reasons for why they're not exactly it, but that's a pretty good measure. That's a pretty good measure of the size of the file. Okay, so basically, whenever you have a bitmap, okay, basically, if you're told that the bitmap is n pixels, okay, by n pixels, so one is the number of columns, okay, and the other one is the number of rows. It usually does columns first and rows second, but it doesn't matter. Okay, so if it's if the picture is n pixels by m pixels, so n by m, and you want to say how big is that file, you take n times m, and that tells you the number of pixels, but then you have to multiply by 3. Why? Because each pixel is 3 bytes. Why 3 bytes? Because each color is 3 bytes. It needs 3 bytes to encode it. So here's another example. This is a kind of question that you could be asked on a test, okay, or on the assignment. If your picture is 1,600 pixels by 1,200 pixels, so usually we would say that a 1,600 by 1,200 pixel bitmap, okay, like that. You'd say, how big is that? All right. Well, first you would multiply the 1600 by the 1200 and then multiply that by 3 and you would get this number here. All right. And let me put some commas in there so it's easy to see. That's going to be 5,760,000 bytes. So 5 million. Million, if you go back to that table up above here, all right, this table right here, you can see that million is basically mega. And so when you say 5,760,000, you're saying 5.76 megabytes. Okay, so over here, all right, where is it? Right here. Okay. When you multiply out the number of columns of pixels by the number of rows of pixels, then multiply it by 3, you're going to get 5,760,000 bytes, which is basically 5.76 megabytes in size. Okay. Now, if that was a little bit much for you, that conversion, don't worry. I'm going to have a tutorial video which will do a lot of word problems in that and this sort of thing. Okay. So there we go. That's how you calculate the size of a bitmap, or can estimate the size of a bitmap. Again, it's the number of rows of pixels, sorry, number of columns of pixels multiplied by the number of rows of pixels, and then multiplied by 3 because each pixel needs 3 bytes to encode a color. All right, one last thing, and then we're done with the theory of encoding, and that is the business of compression. Okay, so what is compression? All right, it turns out that bitmaps and a lot of multimedia files are actually, if you just encode them in the raw, like the bitmaps are, they have more information than you can possibly handle as a human being. And you go, well, why? Why does it have more information than you can handle? And if we go back to this picture here, you'll see that, this region here where my cursor is, it's almost all red. Okay, there's a little bit of variation of the red. It's darker red up here and lighter red there, but it's mostly red. Okay, and then like the signpost here, it's mostly white. Okay, so the colors don't change very quickly from one color to the other. And so rather than actually encoding the entire picture like pixel by pixel, you can actually do like averages. Okay, and these averages, what they do is they decrease the amount of information in the file, but they don't decrease it so much. They make the file smaller because the amount of information in the file determines the size. But what winds up happening is the file gets smaller, but you can't tell unless you compress it too far. Okay, so basically the idea of compression is by doing these kind of local averages. Okay, and that throws away some information, but hopefully you don't throw away so much information that you as a human being can tell that that information was thrown away. Okay, and it's basically a mathematical technique, which I don't have to go into, but I can give you a little sense of what's going on with compression. If I had the grade of every single person in the class, that would be all the information about the grades in the class. But if someone said to me, just give me the average grade, I could say, well, the average grade was like, I don't know, 85. That doesn't tell you how any individual person did. It just tells you how the whole class did. So it kind of does this like overall average of the entire class. Okay, and that's exactly what's happening in this picture here. What you do is you just choose an area of the picture and you go, you know what, rather than me giving you the value of every single pixel, I'm going to give you the average in that area, and that should be good enough. Okay, and that's basically this technique of compression. Now, is it useful to compress? Yes, if you don't want to overdo your space, make your file too big, all right, then you want to do some compression. All right, now usually that's done for you, but just so you know what this compression is all about, you can see that I actually have 4 different levels of compression for this file, which I'll show you in a minute. Okay, so the original file was, I should put bytes after all of these. Okay, bytes. The original file was 149 kilobytes. Now bitmaps don't compress, but JPEGs do. So I converted it from a bitmap to a JPEG, which is just another type of image. And I compressed it, and I got it down to 7.6 kilobytes. From like 149 all the way down to 7.6. So that's quite a bit to go from 100 down to, like, say, if you round this off, that would be like 8. To go from 149 down to 8. That's a lot of compression. And yet you'll see in a minute that you can hardly tell the difference between the two. Okay? Then I compressed it further. I compressed it to 5.5, and you can just start to tell that something is wrong, that that it's starting to lose some of the quality. Okay, and then you can compress it further. I compressed it further down to 2.6, and at 2.6 you can definitely tell that this is a poor quality picture. And finally, when you compress it down to 1.6, it looks terrible. Okay, and I did that on purpose. So the point is that the 149 is overkill. Okay, and the reason it's overkill is because it's got like all the information for the colors of each of the pixels. But remember, that's not all you need. What you really just need is like averages, local averages, because you're not interested. Again, my example of the classroom, I'm not interested in how any particular student did. I just want to know the class average. Fine, one number is enough. Okay, instead of 10 numbers, one number is enough. Okay, so here it's the same thing. Basically, I'm saying, look, you know what? I don't need the color of every single pixel. The color of a region of pixels is good enough. That reduces it quite a bit. And even though it reduces quite a bit, it doesn't make that much of a difference in terms of how we see it, but it makes a big difference in terms of the size. However, if you keep compressing, and again, compressing is doing these averages and making the file smaller, so you are throwing away information. At first you can't, the human eye just can't see that it's a lower quality, but as you get smaller and smaller and smaller, eventually the quality gets so poor that you can tell. Okay, so let's go through them. I'm going to do, let's go back to the original. Okay, and let me change it back to this size right here. Okay, so this one is the original bitmap, and it is 149 kilobytes in size. Okay, 149 kilobytes. Let's switch to this one. Okay, and you probably going to look at that and you go, I can't tell the difference. That's right. You shouldn't be able to tell the difference. Okay, that one is actually 7.6 kilobytes. So we went from 149 all the way down to 7.6 kilobytes, and yet there was hardly any change in the quality, not so much that you could tell the difference. Okay, well, let's go to the next one. So the next one is 5.5 kilobytes. So now we're going from 7.6 to 5.5. Okay, and I'll tell you when that switch occurs. There. And you still might not have been able to tell. Okay, now I can barely tell, but I'm in front of the screen. Okay, and let me go down the next one. So the next one is going to be 2.6. So now we're going to go down to 2.6, and I'll tell you when I'm going to switch, because you should really see the change now. There you go. This one is 2.6, and so what you should notice is the red there. Notice how there's like all these kind of like big squares in there and blotches. In fact, let me zoom in on that one if I can find it here. Yeah, let me zoom in on this one. Okay, I think you can tell that like you can't even read the letters. Before you could read the letters, but now you can't even read the letters. Or look at the car, it's all messed up. And so you can see that there are still some pixels there, but they're like pixels within pixels, because basically what you have are these like 8x8 blocks, and those are the blocks of averages. Okay, and so it kind of blocks it off into groups of 64 and does just an average on those groups of 64. And so yeah, that's at this point, when we've gone down to only 2.6 kilobytes, you're definitely starting to see that the quality degrades. And let's go all the way down to 1.6 kilobytes, and I think you're going to see that the quality degrades even more. Okay, and so here we are at 1.6 kilobytes, and it's pretty messy at this point. Okay, so there you go. That's the story with compression. Okay, so basically, this is the original. So that's, I guess, as good a quality as you're going to get. Okay, and this is compressed, but excellent quality. Okay, still excellent quality. The next one is compressed more. Okay, compressed more. And I wouldn't say excellent quality, I would say good quality. Okay, all right. The next one is compressed even more. All right, and now we're at poor quality. And the last one was extreme compression. Compression like that. And now you have extremely poor quality. Okay, so what are you seeing here? The more you compress, the lower the quality goes. The more you compress, the smaller the file, the lower the quality. You can get away with it for quite a bit. You know, like that's quite a lot. You know, you're saving quite a bit of space there. All right, but then when you go beyond a certain point, it becomes just intolerable. Now, that's it for the lecture. But before I end this, I'm going to say that we're going to be doing some word problems with these. I'll make that part of a tutorial video after this, okay? But basically, because of the compression, we're not going to actually be doing the calculation like of the sizes of files like we did for bitmaps. You can, okay, but the compression, you know, it's on a continuum. You could have a lot of compression or very little compression. So generally speaking, we're just going to use this table right here, okay? And what's that table say? That table says that basically, like just roughly speaking, you'll see what the word problems are in the next video. You know, basically an image, like a low quality web image, is about 100 kilobytes in size, okay? So if you take a look at a web page, you know how web pages have images in them. A typical web page image is only about 100 kilobytes in size. Now, a really high quality image, it might be in the megabytes, but we're just going to talk about low quality images, about 100 kilobytes, okay? A video, like a 2-hour movie, all right, that's about 4 gigabytes in size. That's like DVD quality, okay? And then audio, okay, you know, I didn't show you how audio is encoded, okay? But audio, if you were to encode audio, 5 minutes is like 5 megabytes in size. In fact, probably a better way to think about this is it's basically 1 megabyte per minute. Okay. Now, the reason I say it that way is because you know, like if you were in the classroom, we're not in the classroom, we're online, but if you were in the classroom and you were recording a lecture, okay, you know, for each minute of lecture that you're recording, you would need about 1 megabyte of storage. Okay, so you know, every minute that you record, 1 megabyte. 50 minutes of lecture, 15 megabytes. 30 minutes of lecture, 30 megabytes. 55 minutes of lecture, 55 megabytes. Okay, so that's probably the best way to think of audio. Audio is 1 megabyte per minute. Okay, and then finally, documents. It depends on the document type. Okay, so there's 3 different document types that you should know about. One of them is just TXT. That's the extended TXT. Plain text, another name for plain text is ASCII. Okay, so I put both words there because, you know, you might hear it called plain text sometimes, or you might hear it called ASCII text, but it means exactly the same thing. One page of text in ASCII is about 1.5 kilobytes, and you might say, well, could we have calculated that? Yeah, actually you can. Okay, there are about 250 words per page. And each word in English is about 5 letters, but then 1 space for 6. Okay? And if you do 6 times 250, you get 1,500 or 1.5 kilobytes. Okay? Now, a Word file, because it's got a lot of extra stuff in it, 1 page of a Word file, like a docx file, is about 15 kilobytes. And PDF, this is a bit big, but PDF is kind of hard to estimate. PDF files are, and you'll see them later in the course as well, PDF files are high quality documents. They're like textbook quality documents. Like if you ever download a textbook in PDF format, you know, if you ever download a textbook, it'd probably be in PDF format. It's roughly about 100 kilobytes per page. Okay, it can be less if it's just text, but a lot of the textbooks I have are like physics textbooks with all sorts of mathematical symbols, and the more fancy stuff there is in the page, the more the kilobytes will increase. Okay, so that might be a little bit on the high side, but we'll go with that number. Okay, so next lecture, which will be a tutorial lecture on doing word problems on all the stuff that I've done up till now, we'll be using these numbers here, okay, to, you know, estimate the sizes of a of a book, estimate the sizes of libraries, estimate how many movies you can get on a hard drive and stuff like that. Okay, all right, that's enough for this lecture. Bye bye.